Hello. Hello. So this lecture, as you can see from the name, is on uh, trapology of coatings, and it is actually meant for mainly for bio-based applications. So this is the topic now. Trapological coatings. Uh, to understand what is a tribological coating, first we need to understand what does the word tribo mean. It means basically frictional wear. When we have two different surfaces when they are in contact with each other, the mechanical phenomena that takes place that comes under the term tribo. Now, when we talk about tribo coats, it is basically we're talking about the tribological coatings. Now, these tribological coatings are mainly there to protect the surfaces from the interactions that are taking place, right? If you want to have a protection of the industrial tools, you need to apply a tribological coating, and you need to avoid any sort of wear and abrasion going on that is harmful for the tools, fracture, that is the crack, growth and propagation. And if you go to little downscale devices, then you need to you can also the tribocates can be also used in micro electromechanical systems or nano-electromechanical systems, and it is also used in the case of biomedical implants. Now, to give a brief idea of what a tribal coat is, the hardest known material is your diamond, and so we try to reach the hardness of the diamond by different techniques. We do have some uh, materials which show good hardness and which are used in applications where hard materials are required. Formation of nanocomposite or multi-layers are also being done to increase the hardness and the toughness. So this is actually the brief profile of the different materials, and if you the applications are mainly the applications mainly are, as previously mentioned, in the case of protection and wears towards mechanical effects, like whether it is protection against wear, protection against, and also that includes also chemical effect, that is protection in the chemical corrosion that is taking place. Now, what we focus here is little unconventional from the usual applications. We are focusing here on the biomedical aspect of it. So if you take consider the bioimplants, there are different types of bioimplants. The most common of them are either this orthopedic implants or cardiovascular or dental. These are the three areas where implants are being used most. So when the implants applied to these three areas, they suffer some certain sort of degradation. They fail at certain instances. For example, the cardiovascular stents that is applied, they suffer from thrombosis and restenosis. By thrombosis, it basically means clotting, blood clotting, and by restenosis, it means the shrinkage, re-shrinkage of the stents. So the stents are basically used for a free blood flow. If the stents shrink again, then that's a problem. And the hemocompatibility, that is the compatibility with the blood and other body fluids, accompanying body fluids. So it requires also ionic conduction and biocompatibility in total. And for the dental and the orthopedic implants, where mechanical force and corrosion or interaction with chemical substances take place, we require those implants which avoid wear and wear debris. Where debris will occur only when a certain amount of wear has taken place. So the debris are harmful for the body, and also any sort of corrosion resistance needs to be avoided because the implants are in contact with a lot of body fluids. So these are the areas where this bio or tribal codes are applied. Now, if we talk about tribal codes, mainly hydroxyapatite, that is HAP, is mainly applied for orthopedic surgery or orthopedic implants. HAP is also applied in the case of dental implants. But there are some applications of bioimplants, like if you want to replace a cervical spine, or you would like to replace any other parts, replace something anywhere, a pacemaker, for example. So these sort of these sort of implants, they require those properties of materials which show conductivity and also which are little resistance towards any sort of external stimulus. So in that case, titanium and its alloys are quite applied as bioimplant materials, and we can also have some different type of composites related to these sort of materials, like composites comprising of titanium, carbon, boron, silicon to some extent. Okay, so that is why. So let's come to our objective. What is our objective? Our objective is to analyze the failures at the surfaces of the travel codes already that has been applied, and we are trying to interrelate the growth parameters. I mean, by growth parameters, we mean when the travel codes are being applied uh, uh, and when they have finished, will have certain properties. So basically, structure mechanical properties, that's we are aiming at. So to do this, we are doing coatings comprising of a combination of these few elements, and then we will perform the microstructural investigation, and we will correlate with the different mechanical tests, which includes damage and fracture. And also we will try to understand if there is some tip sample contaction taking place, and what are the aspects by which it gets affected. So the films were deposited by a very usual standard process of Mantron sputtering, where we make targets, uh, of silicon carbide and titanium diboride, and we put them as targets inside the chamber, and we create a plasma. Then we supply argon and nitrogen gas, nitrogen for reactive sputtering, and if we don't want any reactive sputtering, we simply apply argon, and we do the coating for a certain amount of time. Keep the coating thickness a little high because we need to do the fracture and the failure test as well. After the coatings have been deposited, we can find the thickness of the coating by surface profilometer, where we get the step height. Uh, that is, if we put a mask while deposition, a step size formation takes place, from where we can find out the thickness, and we can also find out the roughness of the material. Okay. So after the coatings have been deposited, the microstructure of the coatings were done, and we can see a formation of nano-sized grains. Formation of some Kikuchi pattern-like structures also took place, and the SADP pattern gave that there has been some sort of formation of nanocomposite structures. So the dot patterns, they represent second crystals, while the hollow patterns are near amorphous materials, nanomaterials. So this is what it is, actually a combination of different types of crystals that have taken place. We perform a surface profile-o-metry to find out the interpositional distance. I mean, if there are two grains, the distance between them is 220 nanometers. Now, stress again can be determined through the Stoney's equation, a very well-known equation. Uh, for this stress to be determined, the parameter that is required is the curvature. So whenever a film is getting deposited on a substrate, there is a difference in the coefficient of thermal expansion. I mean, there is a difference between the lattice parameters, and the difference increases. Difference is a function of temperature as well. So if there is, it can be a positive value of radius of curvature and negative value of radius of curvature, difference of radius of curvature. So they all indicate whether the composition is a tensile stress or a compressive stress. So this is the formula. Then we perform the nano-indentation tests of these materials. This is based upon continuous stiffness mode. Materials, we use a Berkovich indenter, and we find the hardness from the projected area. So these are the different hardness and modulus that was obtained. Hardness of 19 GPa was obtained for the coating, and corresponding elastic modulus of 190 GPa. And we have found out the stress strain plot from the load depth plot, and we found the yield stress to be 17.5 MPa. And another interesting aspect is we have found, if we magnify the load depth plot, we found that there has been some discontinuities in the load depth. So these are basically the shallow cracks that get developed on the surface. So this can represent the different sort of cracks. Again, the damage and fracture of these coatings were done. Now, there's a difference between a damage and fracture. The damage actually is the one which is due to an enhanced plastic deformation. So when we are doing the coating, say if this is the surface and we are doing this indentation, there will be initial high amount of plastic deformation that is taking place. So the ratio of there will be a change in elastic modulus also with respect to the increased amount of plastic deformation. And so E is the initial value of plastic deformation, initial value of elastic modulus, and EI is initial value, and E is the subsequent values that we have obtained. So the ratio between these two gives us the damage parameter. So we plotted the damage parameter with respect to the depth, and we found that the damage is a maximum at a certain depth of 12 nanometer. We call this one as the effective depth at which the damage is the maximum. Okay, now an increased value of depth, an increased value of load at certain times causes cracks or causes a brittle failure or fracture. Like now, the geometry of an Berkovich indenter is different from a Vickers indenter for that matter. So even if we are seeing some sort of cracks, the stress distribution is totally different. So in the case of an indenter, but using Berkovich indentation, this is how the cracking takes place. So first of all, there is a delamination of the coating, and there is formation of delamination, and then there is lateral crack as well as different type of. Okay, so we did the final element analysis. That is, we divided any complex shapes can be divided into different meshes, and the stress distribution of each mesh can be found out to find out the different stress distribution. So you can see that there has been a concentration of stress in some areas, which actually during indentation, which actually gave rise to the different type of cracks. The scratch test was performed, adhesion tests, and it is based on increasing the scratching with the ramping load and finding out at what particular depth or distance the film fails. And we compared this failure with different types of scratch profiles, and we found that this is basically spallation and delamination taking place, and formation of cracks was also observed. Okay. Now, lastly, conduction of between the tip and the sample is an important aspect. That is also very much existent, very much important for the case of Tribological, and we found out the conduction, hampering of the conduction by load. If there is a formation of crack, then that means crack means there will be a change in load during the indentation for a very short time. For example, you can see here there has been a change in load. The discontinuity of the plot shows that there is a sudden change in load, and from where we can actually find out the impulse that arise at this stage due to the formation of fracture. And this impulse is responsible for any sort of electrical hampering or electrical conduction that is taking place. So the conclusion is that this the shallow depth, there is a shallow depth heterogeneity existing at any tribal cord, or for that matter associated surface, and which is detrimental for the coating performance. And the stress distribution at the interface were determined, which led to various film failures, and electrical conduction was found to get affected by the fracture. And it is basically on a greater note, the study basically emphasizes that we need to do we need to take some preventive measures to avoid these sort of failures that are taking place, especially for biocodes or any driver codes.